Now, the first thing I want to talk about is what kind of sources are out there that we can potentially detect, at least those that we are aware of. There may be more, of course. The one that you're probably familiar with, because we have detected it already, it's a compact binary coalescence, which is, for their friends, is called CBC. This is two compact objects, like two neutron stars or two black holes, which in spiral, they lose energy through gravitational wave emission. Hence, it's a runaway process. They get closer and closer and emit more and more gravitational waves until they merge in a single final object, which could be a black hole or a neutron star, depending on the masses and a few things we don't know. So this is what we have detected, and it's what I'm going to focus about today for obvious reasons. There is more. A priori, anything which has a non-zero or non-constant, rather, quadrupole moment can emit gravitational waves. So anything which is a violent explosion, like a core collapse supernovae, can emit gravitational waves. A pulsar, as long as it's not perfectly spherical, if it has a small departure from symmetry, like a small mountain of a millimeter or so, it will produce gravitational waves. And then there is what we call the stochastic background, which is represented here as a rainy surface of a lake. And that is basically the sum of all the sources which, taken one by one, are too weak to be detected, but all together could give a measurable signal. Now, as I said, all of these are sources that we expect to see in the next few years. Some are weaker than others, so it may take a bit longer. And of course, the most exciting thing is the unexpected, which hopefully will happen one day. We'll get something and we have no clue what it is. Now, until that happens, I'm going to focus, as I said, on compact binary coalescences. And so the two components objects are, as I said, neutron stars and black holes. I'm mostly showing these slides to introduce the two acronyms that will be used very often in this talk, neutron star, NS, and black hole, BH. You all know where they come from. They are the last stage of the life of massive stars. And the reason why we, or at least I, like them, it's because there is still a lot that we don't know about these kind of objects. For neutron stars, we know that they are basically the most dense objects we can see in the universe. And it's 1.5 times the mass of our sun worth of stuff packed in 10 kilometers or so. So it's extremely dense. And the truth is that we don't really know how matter behaves in these extreme conditions. If you put that much stuff in this small volume, we don't know what happens. They're called neutron stars, but we don't even know whether they're really only made of neutrons or there is more. Probably there is more. And another question, which was an open question for decades until we solved it until last year, I'll go back to this point later, is that astronomers thought for a while that neutron star binaries, so if you take two of these neutron stars and you smash them together, they produce violent electromagnetic emissions called gamma ray bursts. We were not sure until 2017 when we have proven that that is indeed the case. We have also shown that neutron star binaries produce most of the heavy metals in the universe, like gold and such. And a related topic to the composition is that we don't know how large a neutron star can get in terms of kilometers, like its radius, and we don't know how massive it can get, how heavy it can get before it becomes a black hole. These are all questions that we can address with gravitational wave observations. And for black holes, it's even more extreme. The only thing we know, basically, is that they are even more massive and they're more compact. The thing that we don't know is that they produce gravitational fields which are pretty extreme. How fast can they spin around their own axis? There is a conjecture that gives you that tells you there is a limit. It's not a theorem; it's a conjecture. We'd like to show that. We don't know really how massive they can get. We have found black holes of 10 solar masses and millions of solar masses. We don't know if there is anything in between and why or why not. I mean, there are ideas, of course. I'm being a bit overdramatic. And we would like to know where and when they form, meaning which type of galaxies, which kind of environment. And also, as I said, they produce extreme gravitational fields. Is it the case that general relativity holds true near these kind of objects? And again, all of these are questions that we can try to address with gravitational wave observations. Now, my talk is made of 3 parts. The first one is called gravitational wave anatomy, because I've been told that I was going to talk with an audience which had very different backgrounds. So I want to give you at least an idea what matters and which parameters we can go after. So the basic picture we have on mind when we talk about a binary coalescence is something like this. There are two compact objects, like two black holes in this case. They each have a mass, they have a spin, which is a vector, and they orbit. This is the angular momentum. We look at the system, say, from here, some inclination angle. Now, if you look at the energy emission to gravitational wave, it's not uniform. There is more energy going along plus and minus L, and less energy emitted along the plane of the orbit, which will be important later. We'll tell you why most of the system we observe seems to be oriented this way, with L pointing at us, because we can see them farther away. They just send more energy. Now, ideally, we would like to measure all these parameters, of course. I would like to measure the two masses. I would like to measure the two spins, the orientation of the spin, and the angle that the spin forms with L, and so on and so forth. In practice, some of these are harder than others. And what we can do better is measure some combination of these parameters. For example, instead of measuring very well the two masses individually, we can measure much better this combination, which is called the chirp mass. It's a combination of M1 and M2 and the total mass. Same thing for the spins. We would love to measure spin 1 and spin 2. In reality, we measure very well this spin effective, which is basically the projection of the spin along L. Okay? And I mention this now because these are some of the quantities that you will find reported if you read LIGO's paper, and now you know why, because we measure those better than the one that ideally we would love to. Okay, now, so that's what our system is made of and the kind of parameters that we are after. I want to also spend a minute or so talking about how each of these impact the signal we see here at Earth. And I'll do this in a slightly tangential way, starting with the Planck spectrum of the CMB. And the reason I'm doing this is because when I was interviewing for my job at MIT, one of the faculty drew this in the blackboard, and he told me, if I look at this, from each of these features, I can tell you something about the universe. Now I want you to draw a gravitational wave and tell me what you learn from each feature. And it was actually very, very instructive, so I'm going to do this for you. This is I forgot about this. That's how fancy I get in terms of animation. This is the reconstructed gravitational wave corresponding to the first signal we detected in 2015. And as I said, it's a binary system. The two objects are far at the beginning. They get closer and closer until they merge and they form a single black hole. This is the waveform that this system emits. Now, from each of the features that you see, or you may not see in this case in here, I can tell you something. For example, from the time scale, this system only lasted, point something seconds from the time it entered the LIGO band to the time it's gone. From the fact that it's so short, I can tell you that it's something very massive. It's not going to be a neutron star binary. It has to be black holes. It has to be big black holes. And the reason why it's, the same reason why a lot of electric charge emits electromagnetic waves faster than small charges, right? Our charges are masses. So bigger objects emit gravitational wave more efficiently and hence collapse, faster. From the fact that the amplitude is going up monotonically in this phase, which is called the spiral, without any modulation, I can tell you that either the spins were small, or if they were not small, they were aligned with the angular momentum. From the overall scale, I can tell you something about the distance. Actually, a combination of the distance and the inclination, because both affect, as you have seen earlier, the emitted energy. And finally, from the last few cycles here, basically from the moment the two black holes merge to the moment they radiate away the excess of energy and they form a single spherical black hole, I can tell you something about the nature of this object. Right? So this is basically how, This is basically how these gravitational waves encode in their phasing, duration, amplitude, and so on and so forth, information about the source. Now, of course, we don't do things by eye. We have sophisticated and CNC and algorithms, but that is much more, I think, intuitive. It's a nice way of seeing what's important and why. So if you do the, the sum of all these parameters, you will notice and discover that a compact binary coalescence system depends on 15 parameters in the simplest case. You have the two masses, the two spin vectors, so 3 degrees of freedom each, 2 parameters for the sky position, 2 for the orientation, and 2 for time and phase of coalescence, and 1 for the distance. This is if you assume that the two objects are points, which is good for black hole. It's not good enough for neutron stars, because neutron stars are made of stuff. So you need more parameters to describe the stuff that they're made of. That adds 2 more parameters. So this is to say that we are dealing with an high dimensionality parameter space. All of these, in general, are unknown when we detect something. So we have to measure all of these at once. That's why we rely on NCNC. I'm not going to go through technical details, but you can ask me later if you want, because part of my work it's this. All right, so then you can ask yourself, which of these parameters is more important? Which one has the highest impact on the signal? And the math, GR, tells you that the combination of the two masses that I mentioned earlier, this Chern mass, is the one that enters the phase evolution at the leading order. Hence, it's typically the parameter we can measure best. Then comes the mass ratio, so it's slightly harder to measure. Then the spins, then matter effects, which means the deformability if we are dealing with neutron stars. And by the way, throughout my talk, I will mention a lot of LIGO-Virgo collaboration paper where some of these points are explained very well. All right. Now, some of these parameters are correlated with each other for reasons that are typically quite easy to grasp. For example, probably the easiest to explain is a correlation between distance and inclination angle. And the physical reason is the one I mentioned earlier. Gravitational wave emission is not isotropic. There is more energy going up and down L and less energy going on the plane of the orbit. But this means that once you detect something, what you see in your detector here at Earth is the overall amplitude. But you can obtain that amplitude with a system which is face-on and far away, or a system which is closer and more inclined. Both of these will give you, at the zeroth order, the same wave. So that's the physical reason why those two parameters are correlated. This is the mathematical reason if you want. I will not go through details. So very often, if you read our papers, you will see that we don't measure distances very well. And that is why, because we cannot disentangle these two parameters in general. There are exceptions. I can talk over them, about them at dinner if you want. Other parameters which are correlated, and that's important too, is mass ratio and the spins. So what I'm showing here, to make the point, it's a binary black hole with 15 solar masses in total. The top waveform has spins which are nearly maximal. They're 0.9 in the dimensionless units we use. And mass ratio of 0.5, so mass ratio of 2 to 1. The waveform at the bottom has no spin and mass ratio of 0.4. So the point I'm trying to bring home here is that by playing with these two parameters, you can obtain signals which look identical. Hence, they are correlated. That will play a role. I'll go back to this point later on. OK, so this is in terms of what's out there and what we hope to understand about our sources and what it's carried, what kind of information our signal carry. In terms of detection, it's not my specialty. I'm not an instrument scientist, but I should say something. Lydia already mentioned that basically gravitational wave detectors are big interferometers. They're Michelson, well, kind of very, very much more complicated Michelson interferometers. So gravitational wave going through will change the length of the arms in perpendicular direction, and hence will affect the amount of light that you get at the photodetector. We have 2 of them in the US, one in Hanford and one in Livingston, Washington and Louisiana. There is a third one in Italy, which is already operational there. And now these 3 detectors I've already observed over the last couple of years. I will go back to it. I want to also show the sensitivity. I won't go in detail in this kind of plot. I just want to tell you that the x-axis is frequency, 10 hertz, 100 hertz, 1,000 hertz. So that's the audio band. And Y-axis is the sensitivity. The lower, the better, okay? The color code, it's the same you see here. So red is Washington, blue it's Livingston, and purple, well, it doesn't match. Well, it matches here. It's Virgo. So the point I want to make here is that gravitational wave detectors are kind of broadband. They cover maybe 1,000 hertz, something like this. And they are most sensitive at around 100 to 200 hertz. Very good. Now, as I said, these three have been online over the last few years with a sequence of data taking in colors here for the various instruments, and blanks, which are commissioning periods. So LIGO started in 2015 when we made the first detection, then commissioning, then the second science run started in 2016. Virgo joined that science run toward the end, which made a big difference. I'll go back to this later in August. Now, as Lydia said, we're not taking data. We're in the middle of a commissioning period. We should restart, government shutdown allowing, in a couple of months for the third science run, where both LIGO and Virgo will be online with a larger sensitivity than we had in the past. Hence, we should get more detection. I'll go back to this later. The nice thing that I also want to mention is that there is a non-zero, actually, at this point, a quite large probability that a fourth detector in Japan called Kagra may join for the end of this third run. So this green thing has been pushed more on the left, which is very nice. OK, so that concludes my kind of introduction on the signal and the morphology of the signals and how we get them. Now, we have already gone through this data taking. What happened? What happened is that we got a bunch of black holes and neutron stars, which are somehow represented here. And I want to, for the second part of my talk, well, the second third of my talk, cover a bit what we have learned from these observations. It will not be exhaustive because it's just, there is too much. So I refer you to a bunch of papers and you can talk to me. So in terms of number, what we have seen in the first two science runs, it's 10 of these mergers of binary black holes. I will use very often BBH for binary black hole, and one binary neutron star, or BNS, which also was detected together with electromagnetic counterparts. Because if you take two neutron stars, you smash them together, they produce both gravitational wave and light, okay, which is extremely exciting. I like this plot a lot because it shows on the y-axis masses in solar mass, and it shows various objects here. Let me focus on the purple. The purple are the black holes that were previously known, previously means before LIGO, through X-ray binary observations. There is a few tens of them. The blue objects are LIGO discoveries, LIGO black holes. The nice thing about our black holes is that for every two, we get a third one for free. You smash them, you get a new one. So this gives you the masses. You will notice something pretty striking. Our black holes typically are much more massive than the black holes that have been previously discovered. And it's a nice and interesting question there, why this so? No, we can talk about it more later. Same thing for the neutron stars. In yellow, you have neutron stars known through X-ray binary observations. And the two orange points here that hopefully you can see are the two neutron stars we observed. They merged, they formed an object. We don't quite know whether this is a neutron star or a black hole. We cannot say based on gravitational wave alone for this event. There are, of course, different claims depending on who you ask. Also notice the very interesting thing here. There is nothing between 5 and 2. So people have suggested over the last many years that there is a mass gap between neutron stars and black holes, which, again, we will play a role in the next few years trying to see if we can populate this gap with detections or if really there is nothing out there. OK, so if you go through these papers, you will find big and scary tables like this, which I will not go through in detail because it's not the point of my talk. The reason why this slide is here, it's, well, first of all, because I want you to know that it exists and where it is. But the point I'm making is that just in a few years, in 2 years, we went from the first detection ever in the history of humanity to starting collecting events routinely. This will become this detection will become much more often made in the third science run. So gravitational wave astrophysics is really going to go through large number of detection very, very soon. This is going very fast. So instead of going through tables, let me tell you first, what we learn about some of these events. These are our detection. The phone number here is gravitational wave, year, month, day. Okay. So let me start to show you, for example, their mass distribution. This kind of plot here shows for our 10 detections, and the neutron star too, hidden somewhere here, the posterior distribution for mass 1 and mass 2 in solar masses. That's 90%. You will notice a few things here. First of all, as I said, our black holes can get pretty large. This purple object here is the July 29 event of 17, has support all the way to 60 or 70 solar masses for the primary, which is a region where astronomers do not even think we should have black holes, or we could have black holes, with some caveat. I'll go back to this point later. So you can see we are starting covering a pretty broad range of masses. You'll also notice something else. Our joint distribution seems to have at least a low mass, this characteristic banana-shaped distribution. And the reason why it is so is because I told you, we don't really measure very well M1 and M2 individually. We measure very well this shear mass. So the narrow distribution, the narrow dimension here in these bananas are the shear mass. So we measure this dimension very well, and we don't measure the individual masses very well. So you have to get through it. For most of our events, I'll go back to this in the next slide, we cannot even tell you very well if our mass ratio Q was 1 or 2 or 4 or anything like that. Our posterior are pretty broad there. Still, we will learn something. I'll go back to this in a second. Then you can ask yourself the question, OK, what happened to these objects after they merge? How big is the resulting black hole? This is what this plot shows. You see in solar masses, the mass of the final black hole that you get for free from the merger of the previous two, and its spin. Again, this is in dimensionless units. 0 means no spin. 1 means maximally spinning. You see something pretty remarkable. All of our black hole, or the final black holes, are consistent to be at around 0.6, 0.7, with some spread. The reason is pretty simple. That 0.7 comes just from conservation of angular momentum. If you take a binary, there is some angular momentum at the beginning. The final object must conserve the angular momentum. And the fact that they all get the same value, plus minus something, tells you that the spin is not contributing very much. The main contribution to the final spins come from the initial angular momentum, not from the individual spins. In other words, our black holes seem to be consistent with having very small spins, and I'll show you that explicitly in a second, but that's a different way of seeing and saying the same thing. Still on masses, I told you, mass ratio is not very well measured. I can show you that more directly through violin plots for the mass ratio. These are, again, all of our events. They are ordered left to right in increasing mass, so least massive, more massive. You see something clearly. We don't measure mass ratio very well. All of our events have pretty broad posteriors. There is some support for all of them at 0.6, 0.8, so even 1. I cannot really point to any of these and tell you certainly, it was not equal mass, or it was 2 to 1. And the reason why I mentioned it earlier, it's correlation of the mass ratio with the spin. You can see this pretty well in these kind of plots. For different events, again, same color code, but these are the lowest mass, and this is the most massive. You see mass ratio, and this chi effective, which was the total spin projected along L. And you see this very characteristic correlation pattern. That's why we cannot measure either of them very well for the moment. This is, by the way, is very well known. I can point you to literature, and you can talk to me later if you want. But now I don't want you to be left with the idea that we cannot do anything, because this is telling you that taken one by one, these events are challenging. These sources are challenging to characterize. But what you can do, which is very instructive, is to say, OK, let me assume that all of these sources come from the same population, or a sum of populations having different subpopulations. What can I say about that? What can I say about the, the top level, which is what is statistically known as hierarchical modeling, right? So what you can do is to say, let me try to infer the underlying distribution of the population using all of my events. Now, we have dozens of papers on this that you can read. There is a reference at the end of my talk. Hopefully, the slides will be available. And this is a nice LIGO Virgo paper, where this is done using the 10 events that we have detected. Again, this is a pretty busy plot, and I don't have a huge amount of time. So let me give you the bottom line here. This is, on the x-axis, the mass of the primary object, which by definition in LIGO is the most massive. So 5 solar masses, 10, 45. And on the y-axis, there is the rate. So how often we think in the universe this black hole of those masses exist, right? So this plot is telling you, are small black holes more common than large black holes, right? That's what we're trying to measure here. And the different colors are different models in increasing complexity. For example, model A, I will not go through the table, they're just there in case you ask, and I don't remember by heart. Model A, the blue one, is the simple one, assumes that the mass of black holes is a power law. And the only parameters that you have are the cutoff, the minimum mass, and the slope, okay? So it's the simplest model. That's why it's so, smooth. And then you add some extra complexity. In model B, you assume that the mass ratio is also a power law, okay? You measure the slope of the mass ratio, power law. In model C, the green one, the most complex, which is, I think, the most interesting in this case, we assume that the black holes that we observe come really from two different populations. A simple power law population, as you would expect from the initial mass function of stars, and a Gaussian distribution that could be there at higher mass because of something called the pair instability of supernovae. There is, we can talk about it later, but there is good theoretical reason to expect that black holes can get as massive as 50 to 100 solar masses, and then you should not find anything else anymore. No matter how large the progenitor star is, it will always create a black hole of 50 to 100. Okay? So the green model tells you that. Let me assume that there is a population which is a power law, and a second population which is a Gaussian of unknown width, unknown standard deviation. I don't know anything. I'll just assume I know the shape, and I measure all the parameters together. What happens? This is what happens. The three models, as you can clearly see here, they are still pretty consistent with each other in most of the mass range. But there are some features which are, in which they differ. For example, the most complex model predicts less black holes around 15 to 20 solar mass than the other, which is, I don't know if I believe it yet. I want to wait for more events. Of course, the more parameters your model has, the more complex it is, and the more sources are required to pin it down. But something that they all agree on is that there seems to be, a limit on how big our black holes are, around 40, 45 solar masses. And this is nice because this is not something we enforce. If you look at this, these are the priors. We allow our black holes to be as large as 100 solar masses, but our detection tells us that we don't need to go that high. There is nothing above 45 or so, which is nice because, as I said, most astronomers believe that between 50 to 100 is as large as black holes can get, before you get the millions or billions solar mass black holes, of course. So even with 10 events, we are already getting interesting astrophysical information.
But if I understand right, your y-axis, it's a log scale, so it's just that they're exponentially rare. It doesn't.
Yeah, of course. We can not say zero yet. I mean, we can have higher masses. There is a depletion. Let me put it this way. There is a depletion. You would not expect them to be zero for another reason, because there is a non-zero probability that black holes can go through repeated merger. So, that way you can always create black holes in that region, but they don't come from stars. They come from repeated mergers. Thank you. That's an excellent point, though. OK, what about spins? Well, first of all, a reminder. So we typically work with dimensionless spins. 0 means no spin. Plus minus 1 means maximally spinning along plus L or minus L. Now, as I mentioned, we cannot measure very well individual spins. unfortunately, at least right now. As we get louder events, we will. We can measure very well this combination of the spins projected along L, the sky effective. This is what is represented here. These are posterior distribution, again, so median and 90% in violin plots, for the sky effective parameter for all of our black hole binaries and the neutron star here. What you see again is that most of them, which will be important in the next slide, are consistent with 0, with 2 exceptions maybe. This event, December 26th, and this event, July 29, which seems to have a preference for a positive chi effective, which could have astrophysical implication. I'll go back to it in a second. All the others seems to be consistent with 0. Now, if you remember the definition, I'm looking at this vector. There are 2 ways in which this vector can be 0. Either the individual spins are really 0, or the total spin is along the orbit. In that case, the projection on L will also be small. And we don't quite know which of these 2 cases we are yet. The other thing you can do with spins, for lack of measuring them individually, you can measure the projection along L, and you can measure the projection perpendicular to L, which is called chi-p. P stands for precessing, because if this projection is non-zero, then the orbit starts precessing because you have a J vector precessing around L. Now, this is this plot. I will not spend a lot of time because it's depressing. The white side is the prior. The color side is the posterior. They are the same. Okay, right now, we are not really measuring this parameter. We are getting, for most of our events, the prior back. We are more numerical in this. If you read the paper, we have things like KL divergency, so you can go back and check for yourself. So why is this important? Why is it a big deal, say, that this guy here seems to be positive and this one too? It's because spins, and in particular their orientation compared to L, can tell you something about the formation channels of black holes. Right now, if you ask your favorite astronomers, they will tell you that probably there are 2 possible ways in which LIGOs black holes could have formed. By the way, every time I say LIGO, I mean LIGO Virgo. It's just because I work with LIGO, so by default it comes to my brain. One possible scenario is something which is called common envelope formation, in which the 2 black holes that we detect have been together as normal stars throughout their whole life. Okay, so they were in a binary system. Then one went supernovae, the other went supernovae, black hole, they merge. Okay? The other possible scenario is where the 2 black holes that we detect did just happen to be in the same space at the same time, close enough that they formed a bound orbit. But they come from different environment a priori. Okay? They have not spent their whole life together. Right? So this is something like dynamical capture on a dense environment like a Gobler cluster, where you have a lot of objects in a small amount of volume. Now, critically, depending on which way your black holes are going through, which channel, you would expect your final spins to be different. If your black holes are formed by a random encounter, you would not expect any preferential direction for the spin. They should just be randomly oriented. On the other hand, if your black hole have been together throughout their life, torques and friction, at least that's what my friends astronomers tell me, align the black hole's spins with L, with the angular momentum. In other words, if you are going through dynamical capture, the spins should be random, but hence, this chi effective should be symmetric around 0. It can be positive, it can be negative, it can be anything with the same probability. Instead, if your black holes come from this channel, the spins should be aligned, hence this chi effective should be positive. That's why we care about what these chi effectives are and whether they're positive or not. So what you can do is that you can use this information to try to classify the channel and then go to your friends in the astronomy department and tell 80% of the black holes in the universe come from here, not from there, which of course is a big deal for them. Now we're not quite there yet, because our spin measurements are not that good, so we need more statistics. So for the moment, I cannot tell you which of this subpopulation it's winning. What I can tell you, with some confidence, that the black holes we are detecting seems to have very small spins. In this plot here, you see the spin magnitude. Again, 0 is no spinning, one is maximally spinning. That is an inference on the population, okay? So the population of black holes are coming from. And median in a full continuous line, 50%, 90%. I'm not going to talk about the dashed line, it's something else. After 10 events, we seem to believe that black holes in the universe, at least the one that we detect, are preferentially small spin, okay? The error bars are still pretty large. We can do much better with more events, which we will have very soon. All right, next up, something which is important going toward the neutron star. So far I talked mostly about black holes. It's localization. Now, gravitational wave sources can be localized in the sky. Here you see a collection of sky maps, again, for our 10 events, black holes, plus the neutron star. And what we typically do, and what we will do again in the next science run, is that we search for black holes and neutron star in low latency. As soon as we have something, we create a sky map, and we send it to astronomers. Actually, it's public. Any of you can download it in real time. You can subscribe to this. You'll receive a phone call at 3 a.m. if you want. And then you can point your telescope and see if there is light coming from there. Now, as you can probably see, at least for our events so far, most of these sky maps are huge by astrophysical standards. They are hundreds or thousands of square degrees, right? There are a bunch of exceptions here. Look how small this is. This is only a few tens of square degrees. This is the neutron star binary. This is also pretty small. Again, it's, I think, 39 square degrees or so. What is the difference between this and everything else? Is that for the ones which are so small, the Italian detector, Virgo, was online. Since we localize by time triangulation, it makes a huge difference. You have 2 sites or 3 sites. So the fact that Virgo went online in August made a huge difference. Without Virgo, we would not have been able to localize the neutron star binary, this guy here, so well. And then our chances of getting the electromagnetic counterpart would have been much, much lower. Now, the nice thing is that Virgo will be continuously online in the 3rd science run. So going forward, our typical sky maps will look like this, not like those, which is very nice. All right, so that's my cue for the neutron star. Let me spend another minute or two talking about this event. I won't go in detail because I don't have time, and you probably have heard this over and over. This August 17 event was the first neutron star binary ever discovered in gravitational wave. Was also the first ever source that was discovered and detected both in the gravitational wave and the electromagnetic band. Again, I won't go in details, but astronomers have detected light at all frequencies, from gamma rays to radio. This was like winning the lottery without buying the ticket. You just find the ticket on the ground, okay? It was unbelievable. Now, you probably have seen these kind of plots, which are very nice. I'll want to spend some time again. These are the sky maps from LIGO, green, with or without Virgo. So you can see the difference that Virgo makes. You go from the light green, which has a second island here, to this dark green. And then this is the map of Fermi, which is a gamma ray telescope, a satellite. And this is from something else called the Interplanetary Network. They found a gamma ray burst. We found the gravitational wave. Optical telescope pointed their telescope, and they found something there which was not there a few days before. That is the optical counterpart. That is the light coming from this catastrophic, for them, not for us. For me, it was a fantastic collision. Right, so this joint detection allowed, a huge amount of studies which I cannot and not qualified to cover. On the electromagnetic side, people spend hours, and you can find dozens of papers about the progenitor of gamma ray bursts. This was the proof that they are, or at least for some of them, is neutron star binary. And you can show that, we have shown that also produced something called kilonova, which is a nuclear decay, basically powered electromagnetic emission, which was hypothesized, and we have shown that it exists, and indeed is associated with with neutron star binary, sorry. And something else, again, which I love, unfortunately I don't have the time to talk about, is that this joint measurement of gravitational wave and electromagnetic waves allowed for a measurement of the Hubble constant without any use of cosmic ladder, cosmic distance ladder. We can talk about it at dinner if you want. Other thing that we can do with this detection we have done is to measure something which I mentioned earlier, the so-called equation of state of neutron star, which is, what I said, it's related to the exact composition and properties of the neutron star. What are they made of? How does matter behave? This equation of state is what tells you that. It also tells you what is the maximum radius of a neutron star, or the mass. Now, gravitational waves carry that kind of information. With gravitational wave alone, even without the counterpart, you can still say something about this quantity here. This is what is shown in these plots here. It's very busy, so I will just go through the main highlights. This is a posterior distribution on the y-axis. Let's just focus on the blue field line. And this lambda parameter, it's what we call the tidal deformability. For today's talk, the larger, the lambda, the larger the neutron star radius, okay? So if your measurement gives you very large lambdas, you believe that neutron stars are very large and fluffy. If lambda is very small, you believe the neutron stars are very small and compact. And our measurement is this blue distribution with the secondary peak here. We favor small lambdas with only one event. The dark gray or light gray lines or shades that you see here, these are different proposed equation of states. So, of course, you can never stop a theoretician. So theoreticians have spent the last decades trying to study possible ways in which neutron stars could behave, and hence, they propose different equation of states, right, depending on whether you put quarks inside neutron star, hyperions, or whatever else. So the nice thing about this one measurement alone with the LIGO and Virgo is that we can start maybe saying that extremely, so equation of state with favor very large neutron star are probably disfavored. We seem to prefer these equation of states. Of course, as of now, I cannot tell you this is the right one. It will take more detections, but we can do it. There is a long literature that you can read. And with a few tens of binary neutron stars, we can really start ranking equation of state and tell you which one is the most likely to be correct. OK, with all this detection, we, of course, also were able to measure the rate of neutron star binary and neutron star black hole. So basically calculate how many of those merge in the universe every year for some amount of volume, which for us is typically a gigaparsec cube. And these are the numbers that you get. I will not go through the plot. It depends a bit on which astrophysics you put on it. But we give the most conservative bound. We believe that in the local universe there are roughly 100 to 4,000 neutron star mergers for gigaparsec cube per year, and a factor of 10, maybe fewer binary black holes. They are rarer. Still, that is a lot. You can take these numbers and you can ask yourself, OK, I know how sensitive LIGO and Virgo will be in the next science run, which starts again. Today, they didn't vote for the shutdown, so maybe we'll not start in April. We'll start soon, we'll see. But you can say, OK, how many of those will we detect then in the next year? That's what this colleague of mine have done. Again, we do Bayesian analysis, so we always have nice plots, but I will go through just numbers for today. So the bottom line is this. Depending on the uncertainty and some astrophysical modeling that you have to put, the most pessimistic scenario is that in the next science run, we'll get at least a binary black hole per month. But there is a 50% chance that we'll get as many as one binary black hole per week. Okay, so we're really talking of tens of black holes per year. And for binary neutron star, it's a bit, they will be less frequent, which you may be confused. I just told you that there are more of them. Yes, but they are smaller. So they have to be very close for us to see them, right? So that's why we will detect fewer of them. But still, we expect probably a binary neutron star every couple of months. And last but not least, at least in my heart, we are still expecting to detect a neutron star merging on a black hole. So not two objects of the same type, one neutron star and one black hole. There is a lot you can learn from this kind of systems. We don't know how rare they are in the universe, unfortunately. All right, let me, maybe in the interest of time, skip this and move to a slightly different topic for the last 10 minutes. I also been asked to talk about what happens after, right? You also have to think about the next steps. And the truth is that for us, incredibly exciting and beautiful, it's what we are doing is, and what we'll be doing is, if you look at how far LIGO sources are, you know, they're kind of here. So if this plot shows you the redshift here and you know how much universe there is as a function of redshift, using basically the star formation rate as a tracer here, and LIGO, it's right now detecting events at z of 0.1, 0.2, something like this. But there is a lot of interesting stuff that happens far away, right? The peak of the star formation rate, it's at 2-ish. Farther away, there is probably the peak of black holes producing globular cluster. Farther away, maybe it's where the black hole from population 3 stars are, and so on and so forth. And as advanced LIGO and Virgo get better, don't get me wrong, we will see farther away. But the farthest we can see for very heavy black hole, it's Z01 maybe, is the gray area. So we will miss all the fun. So how do we, move forward? We have to build something else. Advanced LIGO eventually and Virgo will be limited by their size. They are 4 kilometers for LIGO and 3 kilometers for Virgo. So if we want to detect these sources at higher redshift, we need something else. We are already thinking about a third generation of gravitational-wave detectors on the ground. Now, the ideas we have in mind will result on a factor of 10, roughly, extra sensitivity, which doesn't seem a lot, but basically allows you, I'll show this in a second, to see black holes as far as redshift of 10 and more, and detect a huge amount of sources. I will be more specific in a second, and all of them, or most of them, very loud. Now, the time scale, we're not talking about tomorrow, talking 10 or 15 years. Right, so again, I'm not an instrument scientist, so I will not spend a lot of time, but this is to show you a bit what kind of ideas are out there for the design of these new detectors. The main ideas are just get something that we know that works, which is LIGO, and make it longer. Instead of 4, make it 40 kilometers, go in the middle of Nevada. There is a lot of space, or Utah. Another possibility is to do it just a bit longer, 10 kilometers, but go underground and make it a triangle instead of an L. There are very good reasons for each of these design. In particular, going underground will buy you more sensitivity at low frequency. I told you that LIGO, it starts being sensitive at 20 hertz, maybe. This Einstein telescope will be sensitive at 1 hertz, okay? And there is extra astrophysics there. Anyhow, so what happens if we build those in terms of our sources? Well, this happens. In this plot here, I'm showing the total mass of a source. This is, for reference, a neutron star, and this is the first black hole binary we detected. And on the y-axis, you see how far you would be able to see that source for various detectors. I'll just focus on advanced LIGO. This refers not to LIGO now. It refers to LIGO in 2021 or 2, when it will be at design sensitivity. And you can see what I told you earlier. Once at design, for neutron star binary, we can see them at redshift of 0.1. And for very heavy black hole, a redshift of unity, maybe. If you build one of these, purple or green, you can see neutron stars all the way to redshift of several. And you can see black holes all the way to redshift of several tens. And the thing is that at this point, you run out of universe, and there is nothing here, which is kind of shown, at least for what we believe now. It's shown in this plot. In this plot, you see again the range, how far these detectors can see. They have slightly different names, apologize. Different people were involved. Again, let's focus on O2, which is the run that we just finished in 2017, and this C, which is one of these projected third generation. The points here are where we expect neutron star and black hole to be, assuming some input from a population synthesis model. Okay, yellow is neutron stars, and white is black holes. So you see what I told you earlier. most of the stuff of the universe is a redshift of unity, 1, 2, 3, something like this. After 5 or 6, there is not very much. And now, while with advanced LIGO, we'll start just getting in this distribution, with this third generation, we'll go past it. So we'll basically see all of the black holes in the universe, at least the ones that merge in binaries, right? There are very many differences, but I already start getting late. So I will not go through everything I have in here, but just a few highlights. So a difference, an important one, is that right now, our typical event, it's weak. If you plot the SNR, the signal-to-noise ratio distribution of advanced LIGO black holes, the one, this is not detection, this is projection for the future, it's up, it goes like signal-to-noise to the -4. Most events are weak, and occasionally you get very loud events. With third generation, the opposite is true. Most events will have a SNR of hundreds. So all the things, all the measurements which right now are hard, they will get easier, right? And that includes measuring, I'll skip a few things, measuring, distance, sky position, measuring the masses, the spins, and so on and so forth. Let me maybe just conclude in the last few minutes I have with something which I think is particularly interesting. I told you that we are measuring right now the merger rate, and we get some number. That is the local merger rate. With these events, you can detect more events, because with these detectors, you can say, okay, if I take the rates we have measured and I use the sensitivity of these future detectors, how many black holes and neutron stars will I get per year? Well, this is the number. We will detect roughly a few 100,000 black holes per year and a few millions of neutron stars per year. So if this is 1 year worth of advanced LIGO and Virgo, this is 1.5 hours worth of 3G detectors, to give you the scale. I think pictures are more impressive than numbers. And what you can start doing, though, is something else. This is not just more of the same. You get more stuff, yes, but it's farther away. So you can start doing things like, okay, let me start calculating, say, the formation channel, the thing I told you earlier. Where do my black holes come? They come from galaxy or they come from globular cluster? But now, with this future detector, you can add a third dimension. You can also check how your answer depends on the redshift, for example, right? So you can do something like this. You can assume, by the way, feel free to stop me anytime. You can assume that black holes in the universe come from galaxies. These are different astrophysical prescriptions. And some of them come from globular cluster. Maybe some of them come from population 3 stars, which is the first generation of stars in the universe. And the sum of these contributes to the total merger rate that we see here at Earth. So can we disentangle? Can we say which black holes come from which? Which of these channels is more important? And the answer is yes, we can. This is something that we are looking with a bunch of friends. What you're looking at in this plot is, again, using projection for these future detectors. This is the redshift, and this is the merger rate as a function of redshift. Here I'm assuming that my black holes come from some fraction from galaxies, which is this MD, stands for Maddow-Dickinson, never mind. And another part comes from globular cluster, sorry. So you have two populations that contribute. What you detect is the total, which is the black line. Now, here lines are the true values that we know because that's our simulation, it's our universe. And the colored lines are our measurements for the individual contribution with 50 and 90%. And as you can see, we can measure with this third generation detector both the total merger rate as a function of z all the way to very large redshifts, and also tell you which fraction of black holes come from where. And the most impressive thing, which is probably not written here, is that this is using 1 month of data, okay? Because you get 100,000 binary black holes, okay, per month, okay, which I think is particularly impressive. All right, I go to the conclusion. So the first slide I want to have here is about what's happening right now. I think we can say that we have started, gravitational wave astrophysics. It seems a bit like a cliche, but I think it's really true. With only 10 binary black hole and 1 neutron star, so with a year and something of data, we have already started probing the mass and spin distribution. And started saying something about what neutron stars are made of. Also something else which unfortunately for lack of time I couldn't talk about. We have also done some tests of GR. Spoilers, it seems like Einstein is right. Okay, like everything is depressingly consistent with GR so far. And we have started doing cosmology, measuring the Hubble parameter using gravitational waves. I do some work on this, so although I didn't have time, you can ask me later, we can talk about it. And we have done even more that, there is just only 1 hour. So this is the beginning. As I said, we are going to get data in a few months for 1 year, roughly, and that should bring a few tens of binary black holes and a few more neutron star binary. So I think if I talk to you next year, I think I will be able to tell you that most of the black holes that humanity has discovered come from gravitational waves, not from photons, which is particularly nice. The other thing is that this is beautiful, but it will bring us only maybe to z of 1, which in cosmological scale is our backyard. Okay? If we want, and we do want, to study the other side of the universe, we need something else. We need a new generation of detectors. And those, although I had to run a bit, so I'm sorry about that, will be able to, will allow us to characterize neutron star and black holes, say something about where they come from, and add the redshift dimensionality to our answers. All right, I'll stop here. I'll leave this here because I want to remind you that everything we have done, it's public. You can go here. You get all of our data, all of our measurements. You can do whatever you want. And if those are online later, there's also millions of references that you can, go and look through if you want. Thank you.